Okay, so what we're doing here is going through 4 combination circuits, and I'll be posting this video in both the Electrical 1 and Electrical 2 folders, so both classes, regardless of where you go to, you'll find it. So this video will be separated into 3 parts. The first part is I will be showing the 4 circuits, and if you want to attempt this on your own without any further help, just pause it there, and I will be providing down in the description box links to each of the 3 parts, so you could just skip right to it quickly. So if you think you can do these 4 circuits without any help, just go through part 1, get the circuits, and then skip to part 3, where I will work through the circuits and provide the solutions. And in part 2, what I'll be doing is providing a brief description and way to look at these circuits and to begin to work through. So we won't be doing any direct math. In part 2, I'll just be providing the way to look at this, and then in part 3 we'll get into the math and provide the solutions. Okay, so as you can see here, this is the first combination circuit. This is the second combination circuit. So again, just pause the video, write down the values, and work it out if you need to on your own. Here's the third one. And lastly, here is the fourth circuit. And already we find ourselves in part 2 of this video. So understand the prerequisite information to be able to complete these combination circuits are to understand the characteristics of individually of series circuits and parallel circuits, because unless you can do those two separately, then you'll not likely be able to do these combination or these series parallel circuits. So this is our first combination. So what I'm going to go through here is basically a stream of consciousness, what I think of when I see a circuit like this. How am I going to attack this? Now, in Electrical 1 and for most of Electrical 2, save a few examples, what I will do is I will give you the resistance values of all the various loads. Now in Electrical 2 we switch that up a bit, where you end up, I don't give you a resistance value, but in order to be able to complete our table here, I have to provide you with some other information. So typically it's a current value at some point in the circuit, so you are able to calculate all the various values. So what I've got here, this is circuit number 1. All I've done, and I've placed it in red, so we know the values that we are given are in red, and then the values that we will calculate are in black. So if there's any problems, we know the problems will be in the black text. So when I look at this, instantly you know this is a combination circuit, because you have parallel sections combined with a series section. So understanding that in almost all cases in these courses, I'm going to give you the resistance values. So your first step almost every time is just to calculate RT. So how do we look at calculating RT? Recall that the first step I always take in class is to try to break this diagram down into a simple linear function. So just a math calculation without the actual values, and in this case when we're calculating resistance, you have the 1 over resistance calculations of a parallel circuit. So simplifying that into just a single straight linear function, I've provided you with, we needed an operator, which means in parallel with. So instead of writing, if we wanted to simplify this down to a straight, very short linear function of how we calculate RT on this, I had to provide you with an operator that I made up. specifically for these classes, and everyone is on the same page, so there's no confusion there, and it actually does cut down this linear function quite nicely, and it explains it completely. So recall we have a parallel section here, and that entire parallel section is in series with R1. So if you recall this right here, this is what we've written. So RT equals, resistance total equals R1. R1 is in series with the rest of the circuit. So this would be R1 plus, because resistance in a series circuit is just the sum of. So R1 plus, and then we move into our parallel section. So if we were to write this down, it would be 1 over R2 plus 1 over R3 plus 1 over R4. So that gets a little complicated. Let's just break this down. Now we can't do the math specifically like this, but this linear function breaks it down very simply. So R1 plus, and remember we have to do this parallel section first. We can't say R1 plus any of these resistance values individually. That's a parallel section that we have to complete first to get an equivalent resistance, and then we sum that with R1. So therefore we have R1 plus, and then we start with our brackets. So this is what you've learned in grade school in math with order of operations. So we have R2, and this is the operator that I've more or less made up for you. We needed a way to say in parallel with, so what we have are two lines supposed to be parallel. My apologies for the poor writing with the pen tab, but that's just how it's going to work out. You can still see this. So this means R2 is in parallel with R3, which is also in parallel with R4. So this is this in parallel portion. We only have one resistor in each branch. So this is the 1 over R2 plus 1 over R3 plus 1 over R4 that you would write. But understand, this is how we look at this. So if I just gave you this function right there, you could reproduce. We don't have the values in here because, again, we're not doing the math just yet. We're concentrating on how do we look at this circuit, how do we break this down so you'll come up with the right calculations. So if I gave you just this function here, you could reproduce this diagram just with this. So they go either or, one way or the other. And the only thing that you weren't aware of when you started this class is this little operator here or here. It's just two parallel lines, and that we take in our class to mean in parallel with. So that's a simple function there. So that's how we would look at the first circuit here. Now let's take a look at our second combination circuit. So these are just going to be in order of increasing complexity. For the most part is how I've designed each of these steps, 1, 2, 3, and 4, each of these diagrams. So here's our second diagram. So essentially what we've done here, it's just a slight variation of your first example where we've added a resistor over here, and I'll go through this and explain where I see a lot of people go wrong on their examples. So first of all, just let me provide you with our linear equation here of how we look at this. So again, we've got all of our resistance values, so you can move straight into so I'm just providing this here. There again, we're not doing the math, we're waiting for part 3 to do that. So RT equals R1 plus, because R1 is in series with the entire rest of the circuit. So now let's look at this parallel section. You can see that R2 is in parallel with R3. So you can see that right here. R2 is in parallel with R3. But now this is where if someone's going to go wrong, where they go wrong. Many people will say in parallel with R4, in parallel with R5. Okay, so they would leave out these brackets. Instead of the plus there, they would be putting another in parallel with. But understand, R4 and R5, just look at this section of the circuit right here, from this little connection point to this connection point. Because anything between these 2 points is in parallel with R2 and 3. You can see R4 and R5 are in series with each other. So before you can put this branch in parallel, you have to sum these two. So that is shown up here. So you see R2 in parallel with R3, which is in parallel with, and then before. So you've got nested brackets. Before you can do that third parallel branch, you have to sum the two resistances first. So in this case, 1000 ohms plus 1000 ohms. Okay, and then that sum is in parallel with the other two branches. So that is the explanation of the second example. Okay, so let's take a look at our third example. You'll notice all we've done here is we've got the exact same configuration of the second example, and we've just added another R6 or another resistor R6 here. And there again, it doesn't matter what side, the positive side or the negative side. R6 is still in series with the entire rest of the circuit. So let's take a look at how we would write that. And that's right here. Remember, RT equals. Now what I've written here is I just start at the positive. Remember, just think conventional current flow. This is just how we looked at R1 is in series with, all right, this whole mess here, which is this brackets, which is exactly the same as your second example. And then as you come around, it's in series with R6, so that's where you get the plus R6. Now some of you may write RT equals R1 plus R6 plus, and then this part here, so this R6 would be added in over here. There again, mathematically it makes no difference. You're just doing this plus whatever this works out to. So whether you add R6 on to the end or stick it in before, so R1 plus R6 plus, and then this bracket here, makes no difference. I just choose to go from the positive, work my way around when I'm writing this little function here, and then obviously I finish up with plus R6. And finally, let's take a look at the fourth example. So there again, this is the same as the third example. All we've done is removed the series circuit that was positioned here. So in actual fact, it's actually less involved than the third example. Why I put this in here is because I've seen many times that putting the resistor over here versus over here tends to throw people. So I'm just giving you this example and showing the RT calculation here for those that it'll help. So you're going to understand here RT equals. Now again, I've already explained this in the last couple examples. So this is the same R1. We've just changed the resistor numbers because we no longer have R1 over here. So our first resistor here is this entire parallel section. R1 is in parallel with R2, which is in parallel with the sum of R3 and R4. So that's this nested inner bracket right there. And then they're all in series with R5, so we just put at the end plus R5. Okay, this R5 could be stuck at the beginning. You could say R5 plus, and then this parallel section here. It matters not whether you have a resistor here or here. The calculations are the same. It doesn't matter whether you put it in the front or tack it onto the end. Remember, any resistor that's in this portion of the circuit here or here is still in series with the entire rest of the circuit. So don't let the fact that I just threw a resistor over here and not over here throw you. You'll notice it's the same either way. Okay, now we begin with part 3. I'm going to leave this formula up here so we have a reminder of how we're looking at this. So again, we start with RT. You can see over here I've got a spreadsheet started. So we're going to skip to or move back to the first circuit here. We're going to be calculating the voltages, the currents, and as well as the power. Remember, power is simply volts times amps. So our first step, however, is to calculate RT. So if we just look at this, this is our what you could call our pseudo calculation. That's how we would look at it, but obviously there's some math to do inside of here because simply stating in parallel with doesn't actually use any direct formula. So we have to insert and expand this to actually apply some math to it. Okay, so let's begin. We're going to say RT equals, and let's just start putting in the values here. Now, since these are all in ohms, I'm going to skip putting the units in, but don't forget that some of these other examples have kilo ohms, so you have to remember which unit you're using at all times. So that'd be 45 ohms plus. Now, you can see here, these are strictly, there's no nested parentheses. Okay, so you're literally just putting this resistor in parallel with this one, in parallel with this one. So we use our resistors in parallel formula. Again, apologize for the writing. This pen tab is harder than it looks. So this would be 1 over 50 plus 1 over 300 plus 1 over 150. Okay, and all that is, here, just let me fix this up a bit. There we go. That's supposed to be a bracket. But this is essentially how it is. 45 ohms plus these three resistor values in parallel. So again, it doesn't matter if you want to move straight to decimals or use fractions. I think, for better or worse, most people that I find, many skip straight to decimals, although this would be a pretty simple and straightforward lowest common denominator. I'm going to do this with decimals because I see how many people do it with decimals versus fractions, so I'm just trying to provide the information that is more closely or most closely related to what I see being handed into me. And you folks that use fractions, that's fine. You can continue to use fractions. Okay, so before we do that, however, before we get any deeper into the math, let's take a look at some of our characteristics. It's good to have the ability to be able to look at this and have a general idea of what RT should be. So recall some of our it's a little bit more than just rule of thumbs, but I call it rule of thumb. You know it's an actual mathematical fact of resistances in a parallel circuit. The resistance of this section here will be no greater than the smallest resistance. So you know going into this that this RT is going to be no greater than 45 plus a value. Here's our 50 ohms here, which is the smallest. Now the resistance of this section here is going to be no greater than 50. So you know for an absolute fact that RT is going to be less than 95 ohms. So if you do some calculation, you get some sort of crazy number here, take a step back, and I always say do a sense check. And what I mean by that, sense, S-E-N-S-E. What I mean by that is have a look at this, understand the characteristics, and see if, without actually doing any mathematical calculations, does it make sense? Okay, knowing simple facts of resistors or resistances in parallel. So remember, in the parallel section, you can't have any greater resistance value than the lowest. All right, so you know it's going to be less than 50 ohms. So if we're working through this, and I'm not going to do every minor calculation here, but if we're working through this, just let me find my pen tab here. We know this is going to be 45 ohms plus, and this happens to be 33.33 repeat ohms. That's what this section works out to. Now here again, let's just take a look at this, for example, as an example of something more you can glean from this. Recall I always give you the there again, a little bit more than the rule of thumb. It's an actual mathematical fact that any two resistance values that are the same, that are in parallel with each other, the result of that resistance is 1/2. So for example, if I had 300 in parallel with 300 only, you would know, and you can do the math and confirm it, but you would know going into that two resistance values in parallel with each other, the total resistance of that would be 1/2 of the resistance value. So you know that 300 in parallel with 300, it would be 150. I've also given you some other mathematical facts here about resistance values that are double 1. So in this case, you've got 150 ohms and 300 ohms. So one is double the other, or one is half the other one, depending on which way you want to go. If you have that circumstance, so 300 in parallel with 150 ohms for this example, you know the resistance value of these two right here is going to be 2/3 the smallest, or you can also say 1/3 the largest. So what's 1/3 of the largest, it's a straight 100 ohms. So this section right here, without even pulling out the calculator, and there again, do it to confirm it for yourself, and it doesn't matter what values you put in there. If they have these ratios of one's double the other, you'll get that solution where the resultant resistance is 2/3 the smallest or 1/3 the largest. So you know this section is 100 in parallel with 50. There again, what do you have again? One is double the other. So it's going to be 2/3 the smallest or 1/3 the largest, which in this case would be 100, and that's where you get that 33 1/3 from, without even doing this math. Now here again, I provided you with that process and these specific resistance values for that, just as a friendly helper to make some sense out of this, so you know if you get a calculation, is it within the ballpark of being correct. So, and here again. The real world really doesn't necessarily isn't going to give you these nicely, one's double the other type of resistances. So you'll have to do this in all cases. But I'm just stressing to you that you can have a pretty decent idea of what your RT is going to be in these types of circuits, which are relatively straightforward. So you can use that to your advantage, because the last thing you want to do is to get RT incorrect right away, and because that will ruin the entire rest of the circuitry for you. Okay, so completing that, you'll see RT is 78.3 repeat. So I'm just going to type that in here in our first. Okay, and there again, that's ohms. Now let's take a look at this calculation over here. When you have all of them on the column, you can calculate the remaining one, or on the rows, if we just exclude the power here for a second and just look at simple Ohm's law, voltage, current, resistance, if you have any two, you can calculate the third. So you have VT and you have RT, so you can calculate IT. Okay, so what I'm going to do here from now on, I'm not going to write down all the steps. We're just going to talk about it, and you're going to see the Excel spreadsheet here, and I'm just going to populate that with the numbers. Oops. So IT here is 0.15319, so 1532, and that would be in amps. Okay, that's close enough. If you go to 3 or 4 digits, that's close enough for our examples. No need to get any deeper into it than that. Anything around there will suffice for myself, although I will say go to at least 2, rounding with the third, and I would prefer 3 or so, because once we get into very small currents, if you do too much rounding, some excessive rounding, it's going to give you quite a bit different, typically voltage values, and it's going to look markedly different than the one I would use. So just remember, just don't round too much. So just let me remove this for a moment. I'm going to keep this up here. And again, I'm not going to be doing all the math, or else this video would take significantly longer. But just bear with me here. You can see the example and you can see our spreadsheet. So once we have IT, take a look at this circuit. Alright, if we know IT, it's flowing in this section here, and then from this point to the negative side of the battery. If we know what IT is, using your characteristics that you have committed to memory on series and parallel circuits, what else must have the equivalent value of IT flowing through it? And if you look at this diagram here, this formula here, you can see that R1 is in series with the entire rest of the circuit. So R1 is also going to have that same amount of current. So it's 0.1532, and there again, that's amps. Remember to put your values in. You can leave this in amps, you can convert it to milliamps, but in either case, you have to let me know that you know what you're working in. So that's why I always stress putting your units in. Also, too, it will remind you that amps isn't measured in, or the current isn't measured in volts, and voltage isn't measured in, amps or ohms. It's just reinforcing these meanings. So here again, now that we have the resistance value of R1 that was given, we've calculated our I1. It's the same as IT. So now we can calculate V1. So V1 is I1 times R1. So that works out to 6.89 volts. Now, we started out with 12 volts, and remember, voltage drops as you power a load. So you can start out with 12 here and work your way around, and what you'll essentially find mathematically is we'll have 0 volts left. That's how that works. So if we start out with 12 volts and we lose 6.89 volts, how much do we have left? Okay, doing that math, you have 5.11 volts left. Now, where is that 5.11 volts to be found? It's to be found on, here again, take a look at this equation. You have a series section here, and this entire amount is in parallel. So you have 6.89 volts here, and you have 5.11 volts across the rest of the circuit. Now, the rest of the circuit comprises completely of a simple parallel circuit. So using that characteristic, you know that V2 is 5.11 volts. So V3 is also 5.11 volts. And V4 is 5.11 volts. Now moving on, you see here again, we've pretty much, this should be straightforward at this point. Now all we're finding is I2, I3, and I4 using simple Ohm's law. So I'll go ahead and fill these in now. Okay, so recall all we did is volts divided by resistance to find I2, I3, and I4. Now let's take a look at the characteristics of this circuit here and remind ourselves of another law that we have to use in every circuit to be able to find out the remaining values, and it also checks your work. So we found IT, which was the same as I1. So this was this 0.1532 amps. Now we have the current, the entire current running to this point, and now the current splits. Some will go through RT, the rest will travel down to R3 and R4 once we get to the junction here. Some will go through the R3 branch, and what's remaining will flow through to the R4 branch. Now remember, I call this the teeter-totter effect, where if current increases, resistance in that circuit has decreased, or conversely, if resistance increases, current will decrease. So we've got one law and one characteristic that we have to, if we remember and work this through, it will be able to, there again, fact check ourselves, as well as this will become more intuitive. So let's look at the first law. IT and I1 are the same. Now once we get the current down to this point here, where we are now separating this current into various branches, remember that law is called Kirchhoff's law. So the amount of current going into a point will equal the amount of current going out of a point. So let's take at this first calculation. We have 0.1532 amps going into this point. If we have 0.1022 amps flowing through R2, the balance of the current has to be heading down this section of the circuit here. And there again, Kirchhoff's law applies here. Whatever we have coming down here will be separated. So this gives rise to the calculation of current in a parallel circuit, which is the sum of the current through the branches will equal IT. So Kirchhoff's law will state 0.1532 amps will be flowing down to this point, and then it will begin to separate, but the sum of these three currents will be, in this case, 0.51532. So we derive these three currents using Ohm's law. Now let's check ourselves. Is 0.1022 plus 0.017 plus 0.0341, will they sum to 0.1532? And in this case, slight rounding, they actually, as you see them here, sum to 0.1533. There again, for our calculations, close enough. So remember, use Kirchhoff's law, because that's sometimes the only way that you can move forward. Now in this case it wasn't, but using Kirchhoff's law and understanding it will give you a deeper understanding of how to calculate these circuits, which is a must. But it also gives you a way of understanding and being able to reverse engineer this, if you will, and understand that these must be right due to Kirchhoff's law. Now let's take a look at the second characteristic of current in a parallel circuit, and we call this the teeter-totter. Now if I were to give you any amount of current flowing through here, and I said that current was going to separate between R2 50 ohms, R3 300 ohms, and R4 150 ohms, you should be able to tell me which branch is going to flow the most amount of current. Okay, there again, low resistance, high current, high resistance, lowest current. So you know that I2 is going to be greater than I3 and I4. Now let's take a look. It absolutely is. And which branch is going to have the lowest current? It's going to be the one with the highest resistance. So R3, or in this case I3, will be the smallest current value of these three. And you can see they are. So there again, just this provides you with a deeper understanding of the circuitry, and if you can think through this, it makes your life calculating these circuits infinitely easier. I'm not sure how you could do it without this knowledge, so that's why I point it out on every circuit. Now since this is circuit 1 and I don't want this video to be any longer than it needs to be, in the subsequent circuits 2, 3, and 4, I'm going to just briefly mention that. And I will refer you back to this circuit 1 where I've gone through a little bit deeper details of these particular characteristics. So from here, all you want to do is calculate P. Remember I told you P, power. Okay, it's measured in watts is the base unit. Now for all of our examples in electrical 1, electrical 2, I just tell you simply calculate that last. It doesn't matter what configuration your loads are in. Power consumed is power consumed, so it's always the sum. So in this case, PT equals P1 plus P2 plus P3 plus P4. It will always equal that, so just do that last. You also be aware that power equals volts times current. So in this case, I'm just going to multiply these, right? Sum them and make sure that VT plus or times IT will also equal. So that's our fact check. Do it both ways, and that will confirm that your calculations here are correct. Because without that, without doing that, if you had a bit of a problem here, you'd likely find out sooner than later. But if you haven't yet, this will be the final determination of whether your calculations are correct. So really, if you do all of this, you can determine that your calculations are correct, and I wouldn't even need to see it, because if they don't work out very, very close, you know you've done something wrong. So I'll just pause this video and we'll calculate these. Okay, so P1 is simply V1 times I1, P2, P3, P4, and if you sum these for power, remember energy consumed is energy consumed. There's no perpetual motion machine, so it's always a sum. Alright, if you've consumed power, then you've consumed power. It doesn't matter in what configuration any circuit is. So if you sum these, it comes to 1.839 watts. Remember to put your units in. And as a check, you can do VT times IT, and if you do that, you'll come out to 1.8384. So very, very close, well within our rounding limits. Okay, now let's move on to circuit number 2. Okay, I'll pop out this linear formula or calculation here of RT. So again, to make this video as short as possible, I'm going to let you go through and do the calculations. Refer to circuit number 1 where I detail how this is done. One small difference here, which I will write down for for this second section here, for this second example here, is because this is different than 1, and I won't need to do it for your third and fourth example. Remember, RT equals 45 ohms. Now I will convert these kilo ohms to straight ohms just so I don't have to put any units in. So this is the same, 45 plus. Now this whole section is in parallel, but remember we have this nested brackets in here because we have these two loads or resistors in series with each other, and when you combine them, when you sum them in this case, notice that's what it says right here, then we put them in parallel. So I'm going to write down what that is, and why I'm detailing this is because I see people go wrong here quite often. 1 over 50 plus 1 over 300. Now this is where people go wrong. They see this here and they forget that there's brackets here. So what do they write? 1 over 1000 plus 1 over 1000. Okay, that's where you get it wrong. Remember, these are summed first. So you do 1 over 2000. All right, and that's different than saying plus 1 over 1000 plus 1 over 1000. And that's why when you do that section wrong here, I get that this is a plus here. I can see it when I see your work, and if you've got it wrong, this is where you get it wrong. You say 1 over 1000 plus 1 over 1000. It doesn't work. That's not what this formula says, and that's not what this is. Remember, these two are summed. They're not in parallel with each other. Just after you sum them, they're in parallel with R2 and R3. So this is the twist to this circuit here when you have series nested inside of a parallel. So I'm going to point that distinction out. And from here, I will just quickly do the calculations, and we'll make this shorter here for you. Okay, so working this section out here, it's 1 divided by 0.02383. Remember, we're just going to decimals here. So 45 plus that is 86.958 ohms. You could round this to 87 if you wanted. I'm just going to leave this here, but for quick simple calculations, if you rounded this to 87 ohms, that wouldn't be the end of the world. You would still see that your calculations come very close to what mine's going to be. So I just left this here in case you made any mistakes. You would see that this is likely where you might have went wrong. Now if you actually alternatively work this out, 1 divided by 1 over 50 plus 1 over 300 plus 1 over 1000 plus 1 over 1000, you would see that it would come out to a difference here, and then it would throw your RT calculation off. But again here, look at this. Does this figure, which by the way works out to right here, this section here works out to about 42 ohms, 41.958. So does 42 ohms seem right for this section here? Here again, take a look at this. What's the maximum that this can be? It doesn't matter that this is, 1000 ohms plus 1000 ohms. That's where you get your 2000 ohms here. It doesn't matter that there's that much resistance here. This section here is going to be no greater than 50 ohms because that's the smallest resistance value of the parallel section. So again, you're going to be less than 95 ohms as a what I call a sense check. And 87 ohms is less than 95, so it's probably not that far from wrong. And because you have high resistance values or sections with respect to the lowest, the resistance value of this section, which happens to be about 42 ohms, is going to be pressing up closer to 50 ohms because you've got so much resistance in parallel with it. So that's a bit of a helper, but just remember, you can't be anything greater in this particular example than 95 ohms. So that makes sense that we're likely in the ballpark. There again, we start working with the calculations. When things stop adding up, we know we have to go back and see where we've made a mathematical error. It's fine to make a mistake in math as long as you just catch it, and you catch it by double checking. And if things stop working out right, as long as you haven't made a complete mess of the rest of the circuit, you should be able to catch an error and realize that you've made a mistake before that. So just go back and see where the mistake was made. So what I'm going to do here is just simply explain what to do next, and I'll fill in these values. So obviously we've got 2 of the 3 for Ohm's law, so we find out IT. Once we know IT, using this circuit here, what else has to be IT? Well, what else has to be IT is I1, so you have I1. From there you can find V1, and if you have VT minus V1 is the voltage across the entire rest of the circuit. Now, this is where it gets slightly more complicated, so let's just work out to this point what we've got. We'll fill in the blanks of what we know to this point. Okay, so I've just filled in what I had just described. So we calculated RT, therefore we can find IT. Once we have IT, we can see that I1 is in series with the whole rest of the circuit. You can see it here on this section of the formula. So once we have that, we can calculate V1. Now 12 minus 6.21 leaves us with 5.79 volts left over for the entire rest of the circuit. You can see that the entire rest of the circuit is a parallel section. Now you've got this little series portion within the parallel section. But you can see here that starting out with 12, a voltage drop of 6.21 here, 5.79 left for the entire rest of the circuit, which is across from this point to this point. So you should be able to see that V2 and V3 are completely in parallel with the remaining voltage of 5.79. So V2 is 5.79 volts and V3 is 5.79 volts. Now you know, or at least hopefully by now, so we have 5.79 volts from this point to this point. Okay, remember, you can move your leads anywhere as long as you're not crossing a load. So if I say 5.79 volts between here and here, that also means from this point and this point, or this point and this point, and this point is the same as this point. So if you wiggled your voltmeter leads down, you would see that you have 5.79 volts across here and here. So you can see that these two values collectively, V4 plus V5, will equal 5.79 volts. All right, that's that series section here. Remember, voltage in a series circuit is the sum. So you've got 5.79 volts here and 0 there. So these two values, or resistance values, will share that 5.79 volts in a ratio that is actually the same ratio as the difference between these two resistance values. But if you will learn to understand that. If you do now, great. If not, don't worry about it, because we have a way to mathematically calculate this. Just remember that V4 plus V5 will equal 5.79. We just don't know how they will separate. They separate by resistance values, the same ratios. Now again, I've actually made this one a little bit easier. 1,000 ohms, 1,000 ohms, so they're going to share that remaining 5.79 volts equally, which means you cut in half. So let's not worry how we're going to separate that voltage, although we know now, because we understand the characteristics of these circuits, that it's going to be split in half. So if we do the math, it should bear that out as well. But it's good to know that beforehand. Let's take a look here at our table. Well, let's not worry about that voltage for now. Let's just do what we can do. Just do it one step at a time, and it will all work out. So you can see here we're looking for I2 and I3, and we have two of the three variables, so we can find the third. Okay, so using Kirchhoff's law, we have 0.138 amps coming down this section of the circuit here. In this branch here, we have 0.1158. In the second branch here, 0.0193 amps. And what's remaining? What's remaining is 0.0029 amps. Now, understand that this section of the overall parallel section here is in series. So our current in a series circuit is the same. All right, there's only one branch, so all the current flowing through R4 will flow through R5 as well. So I4 will equal I5, but how we derived what that current value was using Kirchhoff's law. Okay, this current minus this will give us this. Okay, and that's where we came up with the 0.0029 amps, and it will be the same. I4 will equal I5 as well, because they're in series with each other. So now that you've got this variable here, you do have 2, and you can complete what V4 will be. So this is just simply 2.9 volts, and again the same current, and the resistance there is 2.9 volts there. And recall what I had mentioned that, and by the way, this rounds to 5.8 volts, so pretty good. Alright, we didn't do any excessive rounding here, and it worked out fairly close. Now remember, I had mentioned that because these two resistance values are the same and the current will be the same, because that's the characteristic of a series circuit, you would split the available voltage across that parallel section, which was 5.79 volts, evenly. So you can see here we knew that going into it, and then we've calculated it, and you can see it's split exactly evenly. There again, the only reason why that is because these two resistance values are the same. Now, just as a bit of a helper, if this resistance value, say R4, was greater than R5, you should be able to answer the following question. If R4 was greater than R5, which of these two would have the larger voltage drop across them? Okay, pause for effect. The answer is R4, having the higher resistance value, if it did, would have also the higher voltage drop. Remember, voltage drop, voltage shows up on your voltmeter when there is resistance between the leads, wherever your leads are placed. So these two would sum, for example, in this example, to 5.79 volts. If R5 was greater than R4, R5 would have a greater voltage drop across it. There again, it's more than just filling in the blanks, it's actually understanding the circuit. So from here we just move to our power calculations. V1 times I1 equals P1, etc. Okay, so following through with that, you did V1 times I1, etc., all the way down. VT times IT will give you 1.656 watts, and I tried to do a couple extra decimal places here because the current is getting extremely small and I don't want to end up rounding excessively. So if you sum P1 plus P2 plus P3 plus P4 plus P5, it comes to 1.65603. So you can see well within our rounding limits. Okay, so moving on to our third circuit. I will shortcut this massively, and if you can't follow this, they're going to go back to the previous circuit, circuit number 2 or circuit number 1, because there's no sense me going over the exact same information. So if you've been following along through the entire video thus far, you'll be able to keep up. So just to shortcut this video, or else it would literally last hours if I had to re-explain every little piece, because you'll notice these combination circuits, you're literally repeating the exact same process in every circuit. Alright, and some circuits may leave out some processes that you don't have to duplicate, but in reality, once they get anything close to something like this, you're repeating the same procedure over again. So if you can't follow circuit 3 and circuit 4, go back to the previous ones. I've explained the principles already. So here again, the reason for circuit 3 here is just as a bit of a reminder that whether you have a resistor in series with the whole rest of the circuit on, say, the positive side or the negative side, it matters not. It makes no difference. So you're just following through. So this RT is going to be R1. If you wanted to put R6 over here, like I had mentioned before, you could. So R1 plus R6 plus whatever this is. And you know how to deal with two resistors that are in series within a parallel circuit. Okay, so if you follow through, I just did this part for you, so if you made a mistake in this section here, you'll catch it early. Okay, now there again, it doesn't matter if you make a mistake later on. The earlier you catch it, the better, but it doesn't matter. As long as you find your mistake, back up, find out where it is, fix it, it's perfectly fine. Understand here, what might RT be? Well, you know it's going to be, this section here is going to be no greater than 50, and then you're going to sum 25 to make 75, and then another 10 to make 85. So you know RT has to be less than 85. So 68.07 ohms is possibly close. Once you have that, simple Ohm's law will give you the current, IT. Now understand, I1 and I6 are in series with the entire rest of the circuit, so they get the same current. So you can see that here, and from there we work out V1 and V6. Okay, so you get V1 at 4.4075 volts, V6 at 1.763 volts, so 12 minus these two, because they're in series, will leave the remaining voltage left over of 5.8295 volts, and you can see that V2 and V3 will receive the full voltage. There's no other loads in series with the remaining voltage across this section here, so V2 will be 5.8259 volts, and so will V3. From there, you calculate the current going through these two branches, and there again, what do we use? Kirchhoff's law. The current going through here minus that current will be what's left over for I4 and I5. Okay, so dividing or finding I2, V2 minus R2, and by the way, I had swapped a couple numbers here, and I noticed that as I was calculating it, so it is 5.8295, not 59. So the I2 branch will be 0.1166 amps, the I3 branch is 0.0389 amps, so what's left over using Kirchhoff's law is IT, okay, minus this, minus I2, minus I3, will give you 0.0208 amps. And remember, that's I4, and I4 and I5 will have the same amperage, so 0.0208 amps. And then we can find out the separation of this 5.8295 volts, because now we have the current, so it's simple Ohm's law. So since we have the current in this branch, okay, I3 times R3 will equal, 4. I4 times R4 will equal V4. Alright, and using Ohm's law again, you have for V5, 4.16. Now, V4 plus V5 should equal the voltage supplied to this entire parallel section. If you notice, V4 plus V5 does in fact equal very close to this figure here. If you sum those, it's 5.824. Because of rounding, it's definitely close enough. So from here, all you do is V times I again, and you get your powers, and then you do 12 times or VT times IT, and then make sure they sum to the same, and that's your final check. Okay, so doing V times I will give us our powers. If we add them all up, if we sum them, it's 2.1156. And if you'll notice that 12 times 0.1763 within a decent enough rounding error gives us that figure there. So there's circuit 3 complete. Okay, so now we move on to circuit 4, which at this point should be old hat for you. So I'm just going to provide these solutions here because you should notice that this section here is very similar to the other ones, and the only thing we've done differently here is our single load or a single resistor in series is over here on this side versus that side. But as you've already been explained to several times now, it makes no difference to how you calculate the circuit. Right? You're going to calculate RT. From there you can calculate IT, and then from there you can find out what V5 is, and the rest of the circuit will be VT minus V5. Okay, and whatever that voltage is will be applied to R1 and R2, and they'll be applied to the sum of V3 plus V4. And from there, or I should say, you know that V3 plus V4 will equal to the will sum to whatever is applied to V1 and V2. But you will once again use Kirchhoff's law. You'll have IT, and you'll know that I5 is equal to IT. And since we have the voltage across R1 and R2, you can calculate the current and then using Kirchhoff's law, you'll get the current in this branch here, and then you'll have the resistances and the current, and from there you can find the voltages. So what I'm going to do to save some time here is just populate this circuit here, and you should be able to calculate that and figure that out for yourself. So I'm not going to provide any more guidance here on circuit 4 because it's been covered in previous circuits. So if you can't do this one on your own without any further guidance, go back and look at the previous circuits, because everything you need has already been provided in this video. Okay, so completely filled out. Here's your solution here within reasonable rounding limitations.